Okay. Before I ask the question that I want to ask about this function, let me go back and ask a question about an easier function. You don't need to graph this one. What's the slope? 3, right? There's a 3 in front of the x, and that's your slope. This is your y-intercept. So the slope of 3x plus 5 is 3. X squared. What is the slope here? It's changing. Right? What's our general pattern? It starts by our slope over here would be negative. And then it starts to flatten out. So maybe around here it's 0. And then our slope starts to curve upwards again and be positive. So the slope here is changing. So what we want to do is we want to estimate the slope at specific points. So a lot of the ideas of calculus are around applying ideas that we have learned about straight lines, like finding slope or finding area, and applying them to functions that have curves to them, where something like the slope is constantly changing. Let me just pick a point. So let's say we're here. And I want to find the slope at that point. So what is slope measuring again? Change in y over change in x. That's one way of saying it. And that's kind of where the formula comes from. But generally, when we say that something, let's say something has a slope of 5 versus a slope of -5, how is that going to be different? Okay, the direction that it goes. What about a slope of 5 versus a slope of 1/5? How would you describe how that looks? Steepness. So it's a slope of what direction is the function headed in, and how steep is the function headed in that direction. So a slope of 5 is much steeper than a slope of 1/5. And so ideally, what we want to use here is the slope we want. Ideally, the slope at this point. So that means, hypothetically, we could have a line coming off of here that just crosses through this point, crosses through the function at this point, and then goes straight through it. So it crosses through it exactly that one point. And we call that line that crosses through it exactly one point a tangent line. You learned this when we did circles. And we said a tangent line to a circle is a point that crosses through the circle at exactly one point. But the problem with the tangent line is because we only have one point to work with, we don't have a slope formula. Because the slope formula needs 2 points. So we need to pick another point using another point. And that other point that we're going to use, what should our goal be with that point? Like, how should we pick what the other point is that we use? If we want to find the slope at this specific point, let's say I pick a point to the right of it. Do I want to pick, like, let me give two options. So here's point A, and here's point B. Which one do we like better as an estimate for the slope? B. B would be a better estimate. Why? It's closer. So in general, we want to pick a point that is closer. The closer we are, the better our estimate is going to be. And so the point that we pick, we want to be very close to the other point that I'm interested in. And this line, which is called a secant line because it passes through at 2 points, is what we're going to find the slope of. Very close. To the other point. Which means we need to, now that we have 2 points, we're going to use the slope formula. Slope formula is change in y over change in x. Well, let's mark down what these points are. So our first point, our blue point, I'm going to label as, well, we have an x-coordinate of x, and that means that our y-coordinate, we can write, since our function is f of x, we can just say that it's f of x. X f of x. Then our green point is our x-coordinate nudged a little bit to the right. A small amount to the right. And so we're going to add, we're going to just give a letter to this little nudge to the right. We're going to call it h. Which means the y-coordinate is going to be f of x plus h. In other words, the y-coordinate at this value of a little bit to the right of x. Because we're just picking some x-coordinate. We're not saying exactly where it is. Where we're going to get to is that this method should work for any x-coordinate, for any general x-coordinate. I just picked a location on this parabola. I could have picked anywhere and done the same thing and nudge it a little bit further to the right and then given it another point and then drawn this line. That's the idea. So for the slope formula, we are going to subtract the y-coordinates over subtract the x-coordinates. Here we go. Our y-coordinate of the green point is f of x plus h. That little nudge to the right. Minus the y-coordinate of our blue point is f of x. Over, subtract the x-coordinates. X-coordinate of our green point, our x2, is going to be x plus h. And then the x-coordinate here is just going to be x. this can actually simplify. F of x plus h minus f of x. But then x plus h minus x, the x's cancel, and we just have h on the bottom. The goal, just to recap everything that we've done, we are using 2 points that are very close together. And that means that my goal is to make these 2 points as close as possible. Because as the points get closer and closer together, I get closer and closer to just looking at our tangent line that we want. So the closer that this point gets to the actual point that we need, the better the estimate's going to be, and the more it's going to look like a tangent line. So what are we going to use for that? What's a way that we can get closer and closer and closer to a value without actually getting there?
Limits.
We just did a whole chapter on it. It's limits. In other words, we want to make our points as close as possible. So we're going to use a limit. And so I'm going to give you just a minute here. So we're going to have this this slope formula that we got, the f of x plus h minus f of x all over h. But we need to put something here. In our notation, there's a variable that we need to approach a number. So usually we have something like the limit as x approaches 5, or the limit as c approaches -3. So we need something to go here. So I want you to think about what that's going to be. If we want the points to be closer and closer, think about what the variable is that we used for that, and what we want that thing to approach. What do we want it to get closer and closer to? So what variable did we use to stand for that distance away? It was h, right? This h was this little nudge to the right that we did. And that little nudge to the right of the blue point is what I want to get smaller and smaller and smaller. So h is what I want to be in control of. Changing x would change where the blue point goes. I don't want to change where the blue point goes. I want to change where the green point goes. So we want h, that distance, and what do we want it to approach? I want a number.
Oh, small number, 0.00000.
So it's a number that we want. We want to, if we want the green point to be on top of the blue point, that's what we want hypothetically. We can't actually get it there, but that's hypothetically what we want, which would make that distance between the green point and the blue point what? 0. So that there's no distance between the blue point and the green point, and we just have these 2 points laying on top of each other. And then we would actually be able to find the slope of the tangent line. But since we can't actually do that, we're using a hypothetical limit to get it to approach that distance being 0. And this thing is the definition of a derivative. Which is the central thing that we're going to talk about throughout this semester. And what I'm hoping for us to arrive to by the end of the hour is a rule for x squared at any point. We're going to start by looking at particular points, but eventually we're going to say at any point, to find the slope of the tangent line, here's what you do. And we're going to use this definition to get there. But before I do that for x squared, let me show you another example so that it might help make it clearer for you. Let's look at x cubed. So here's x cubed. And we are looking at, again, we can think about how this slope changes. It starts being fairly positive and a fairly large slope, and then it gets smaller and smaller, and then it starts to flatten out. When we hit 0, our slope starts to be pretty much 0. Then it starts to get bigger again. But let's focus on a particular point. So I'm going to focus on 2. And at 2, what would my slope be? And then, now my point's in blue. This blue point is going to be this little nudge that we're going to take to the right. And right now we're taking a fairly big nudge to the right. And so we create this secant line that we could find the slope between those 2 points, like that. But you'll notice it's not quite right. And so what I want to do is to make that h, that little nudge to the right, I want to make it smaller and smaller. And as I do that, that slope will get closer and closer to the actual slope of the tangent line, until we hit extremely small values. So here's 0.1. We're getting to 0.01. And you'll notice it's almost on top of, the blue point is almost on top of the red point. But if I zoom in far enough, you'll see that it's actually not. And that there is this little space in between the 2. And also notice, as I zoom in this far, that this almost starts to look exactly like a straight line. It starts to look more and more like a straight line. But it's still not. If I zoom back out, it's still a curve. It's still x cubed. But as I get closer and closer, it starts to look more and more like a straight line, which is part of the idea of this limit, being able to find the slope of the tangent line. So what we're hoping to get to is the slope of the tangent line. So let's do this at specific points. And what we're hoping for is to eventually get a rule for what this slope is at every point. So as I move through the function, how does the slope of the tangent line change? And how can we get a rule for what this slope of the tangent line is? So let's look at a couple of specific examples here. All right, clean slate. F of x equals x squared. And we're going to find I'm going to use this notation. There's a couple different bits of notation for derivative. I'm going to start with this one, dy dx, because a lot of times you'll see d used as stand-in for that little distance. So this little nudge of x. So small change in y over this small change in x at x equals 2. So let's find the slope of this tangent line at 2. Which is about where my initial graph was. I would say this is about 2. So I would expect the answer for this slope to be positive or negative? Positive, right? This is looking like a positive slope right now. Okay. Limit as x approaches 0 of f of x plus h minus f of x all over h. Remember, this just comes from the slope formula. We're finding the slope formula as my distance between the 2 points gets smaller and smaller. So at x equals 2, that means we want the limit as h approaches 0 of, now we want f of 2 plus h minus f of 2 all over h. So we're using 2 for x here because we were looking at specific points. This should look familiar, by the way, because you did something like this in pre-calc. So what is f of x? It's x squared. This should be an h. So that means we're going to take 2 plus h and plug it in for x. F of 2, that's going to be 2 squared all over h. And I know you did this in pre-calc because pre-calc just did this like last week or 2 weeks ago. I also know because those of you in stats were asking me about it when you did it. So I remember going over these questions with you guys. 2 plus h squared. Remember, this is not 2 squared plus h squared. Right? We have to expand it out. It's 2 plus h times 2 plus h. 2 squared is 4 plus, it's square the first, square the last times together and double. So this is double 2h is going to be 4h plus h squared. So that's my f of x plus h, and then minus 2 squared is 4 all over h. This is still the limit as h approaches 0. Cancel. 4h plus h squared all over h. Oh, well, that means one more line here. That means that I can factor an h out of the top. 4h plus h squared. So I can take an h out and say that this is 4 plus h left in the parentheses. And now we can cancel our h on top and bottom. And now that I've canceled out the h that's on the bottom, I can plug in 0 where I couldn't have plugged in 0 before. Now we can plug in 0. And our answer is a positive 4. So that means that 4 is the slope of our tangent line at 2. Always as h approaches 0, because that's that little distance that we're wanting to get smaller and smaller. The functions are going to change, and sometimes we might plug in a point like this. Sometimes we might want to generally add a general value of x, but it's always going to be the limit as h approaches 0. It's always going to be this general structure. That's not going to change. Let me do it. Let's do one more. Still x squared. At x equals, let's do -3 this time. And after you have done this, see if you can think about how we can find this in general. If I asked you to do this at -5 or at 10, thinking about what the answer would be. Because what we're going to eventually end up with is a general function for, at any point, what is the derivative of x squared? Of x squared. Not all functions. Different functions are going to have different rules. We're trying to figure out what the rule for x squared is going to be. It's working very similar to the last one, so I won't take too long on it. And I'll skip a couple steps. H is still going to factor out. So we'll get to cancel and plug in 0. When we plug in 0, we get -6. So at -3, we got -6. At 2, we got 4. At -5, what are we going to get? It's going to be -10. In general, what's the rule? It's going to be, you're going to double whatever value we have. And so the derivative of x squared is 2x. And now we have this shortcut that just says, just double whatever number you're putting in, and that will give me out what the derivative is. Where does that come from? It comes from when it multiplies out. Let's see, let's follow the -6 and see where it traveled from. -6 here, was a -6 here, was a -6h here. Oh, so it looks like when we square, remember the pattern is square the first, square the last, multiply these together and double. So that doubling is what caused the -6 to get there. Same thing if you look back at the last example. Here's if you travel back through and follow your +4, it's this term right here. That h term, which comes from doubling these two things multiplied together. So that's where we get that rule of 2x from. So eventually we're going to have general rules for all these different types of functions. And that's what we're going to start to look at.